In this video, I'm going to give a high-level description of how a single CPU executes instructions. The goal is not a thorough understanding of the details. Instead, I'm hoping to give you enough information to see why a software engineer needs to know about how the processor works. There are a lot of details that we can talk about later. In this video, I'm assuming that you've seen machine instructions. If not, you might want to watch the video at the top before you watch this one. A CPU essentially cycles through the fetch, decode, execute cycle. It fetches an instruction from memory, it decodes that instruction to figure out what needs to be done, and executes that instruction, and then it starts again, fetching the next instruction. There are two registers that are important for this cycle to work.
Remember, registers are a set of special purpose storage locations that are inside the CPU.
The program counter, or PC, holds the address of the next instruction, and the instruction register, IR, contains the instruction that we are currently working on.
So the fetch part of this is essentially read the memory location the program counter points to and store that data into the instruction register.
While this cycle is called the fetch, decode, execute cycle, there may also be one more piece, storing something back into memory. Because writing to memory takes a lot longer than, say, simple arithmetic, it can also be considered a separate part of the execute part of this cycle. This cycle is so innate to how the CPU behaves that the CPU actually has components related to it. The CPU has a control unit that does the decoding of the instruction and an arithmetic logic unit that does the execute. So, the CPU is the part of the diagram above the line. The CPU has to talk with the RAM, or the memory, to store the information and to fetch the next instruction. This diagram shows the CPU structure that maps to the fetch, decode, execute cycle in more detail. The boxes in this diagram are the functional parts of the CPU, and the arrows show how data flows between them. At the highest level, you can see the fetch, decode, execute, and store parts of the cycle in this picture. Let's start by defining some of the blocks. Memory isn't really in the CPU. This is the circuitry that talks to the memory. The ALU is the arithmetic logic unit. That's the part of the CPU that actually does the calculations we need. The register file holds the registers that the CPU uses to hold the information that it's currently working with. So now, with this increase in detail, let's walk through it. The fetch part uses the address in the PC to fetch the instruction from memory. While that's happening, it's also adding to the PC so that the PC will contain the address of the next instruction. The instruction decode part is kind of hidden in this green box. It tells the registers which ones will be used, and it'll figure out what operation the ALU should do when the instruction gets to the execute phase. The store part is really a memory access part. While this is where we store data into memory, it's also where we read from memory. That means that one instruction can either read or write, but it can't do both. In addition, if we're reading data in, it will go through write back to be put into the CPU's registers. So now that we see the big picture, there's one important detail that we need to notice. There is a whole section of this that is just for calculating the next value of the program counter. This adder's sole purpose is to increment the program counter to get it ready for the next time we go through this cycle. The results of that addition get forwarded through the other phases until the memory access phase. Then it goes into a block that is a multiplexer. That's a big word for circuitry that picks one of its inputs as its output. You can see that, in this case, it has two inputs and one control line.
In these kind of diagrams, control lines generally enter the block vertically, and inputs and outputs are horizontal.
One input comes from the adder that incremented the program counter. The other comes from the output of the execute phase. The reason we need that multiplexer is because there is a chance that the instruction was some sort of jump or branch instruction. In that case, the instructor decoder will pull the address that we're supposed to jump to out and pass it forward, and then the execute stage will pass it forward, and that's the other input to the multiplexer. The instruction decoder will also pass forward a control line telling the multiplexer which new PC to pick. When the CPU is designed in sequential phases, it can actually be working on multiple instructions at once in a way that is called pipelining. One instruction gets read from memory in the fetch phase. That instruction moves to the decode phase, and the fetch phase starts to read the next instruction. When that's finished, everything moves forward, and the fetch of the third instruction starts, and so on. Having multiple instructions in different parts of the CPU is called pipelining. In order to play with the pipeline a little bit more, let's make a simplified drawing. In this drawing, the phases of the fetch, decode, execute, store cycle are the columns, and time goes downward. We start with one instruction in the fetch phase. When it moves to the decode phase, the fetch phase starts to fetch the next instruction. When those move to their next phases, fetch goes ahead and starts getting the next one. After enough instructions, all of the stages are busy. We call this the pipeline is full. When this happens, we're utilizing all of the CPU. Notice that we're completing one instruction every phase, even though it takes 5 times that long to complete a single instruction. We definitely want to keep that pipeline full. But now, let's look at what happens if we have a conditional jump or branch instruction. This code is just a series of statements. I don't really care what they are, except that statement X is a conditional jump. Let's look what happens at that conditional jump. As we execute this code, the pipeline fills, and everything runs smoothly until statement X gets to the memory access phase.
Remember, that's the phase that had the multiplexer that's choosing which value will be used for the next PC.
Right. Suppose the condition says that we don't take the conditional jump. Then the next statement we should execute is S5, and that's the next thing in the pipeline. So not taking the conditional jump doesn't hurt the pipeline at all. Now suppose that the condition says we're supposed to make that jump. Then the next statement that we need to execute isn't the S5 that's in the pipeline. It's S10, which we haven't even started. Everything that is in the pipeline has to be thrown away. That's called flushing the pipeline, and it causes a pretty big disruption in execution. Now we're going to have to wait for the pipeline to refill before we start getting an instruction every cycle again. Since flushing the pipeline is so expensive, CPUs are designed to try to help make that not happen. The first thing they do is to change the behavior for unconditional jumps. These are jumps that we always take. Essentially, they add another path here that has another multiplexer to feed forward the address from a plain jump instruction back to the PC. That lets us only flush one phase instead of all 4. Some processors take that idea even further. For conditional jumps, they will try to predict whether the jump is going to happen or not in that instruction decode phase. They keep a history of whether that instruction's jump has been taken and use that history to make a best guess. If the prediction is right, then we only flush at most one cycle. If it's wrong, we'll have to flush the whole thing, but we might have had to do that anyway. To see an example of why all of this matters, let's look at how if-then-else statements get translated into machine language. Notice that if the condition is true and we execute the stuff in the then block, the conditional jump is never taken, and the jump that we do take is not conditional. That means that the pipeline will never be flushed. However, if the condition is false and we need to execute the else block, then the conditional jump will be taken and the pipeline will get flushed. So, if we know that one of these actions, either the then block or the else block, happens more often than the other, we should structure our code to put the more common action in the then block, because that will make the pipeline get flushed less often. This video has a really high-level view of how a pipeline CPU works. In real CPUs, there are more stages and lots more details and challenges with pipelining. However, This level of detail is enough to show how the code that we write can affect the efficiency of the pipeline. Structuring our code so that we use jumps instead of conditional jumps can help.
Last time we talked about pipelines and pipelining and CPUs, so you gave us a little hint about what might be next on the horizon.
Absolutely.
And branches.
Yes.
Predicting branches.
Yeah, predicting branches. So so the story so far is we have our little pipeline of robots, and I've forgotten how to draw a robot. They have square heads, not round heads, otherwise they're humans, right? And we've got our various conveyor belts, and we've got the shoveling robot at the beginning who's picking up bytes from memory. These bytes encode the instructions, the recipe steps that the computer is going to follow. The next robot in the production line interprets them, I don't know what I'm drawing here, but something like that, interprets them as instructions. And so he now says, hey, I decoded those sequence of numbers. This means please add the number 1 to address 22 or something like this. And then at the very end, we've got a robot, and again, who has a square head, who's actually doing the work of the addition and all that stuff. Right. And that's great. And it's faster. But there's a problem, because every time the end robot discovers that we need to be doing something different if we're going to change which recipe step we're on, and it's not just strictly the next one in the sequence, like for example going back round to the top of a loop, he has to pull the horn and everything has to restart. And that's a shame, because now it takes 2 ticks of the clock before any useful work is done again. So we discussed last time some simple ways of making this work. This time we're going to talk about branch prediction. Most of the things that modern processors do actually involve adding more steps to this pipeline. So I haven't given myself room on this piece of paper now, but there is now a new robot at the beginning of the production line, and that robot's job is to make a prediction. And I think we had some really squiggly eyes that you animated beautifully in the last one.
Wanted to do a crystal ball, but it proved beyond my animation capabilities. So instead, he turned into a hypnotized robot.
Because I said something about it being clairvoyant. It has to predict the future. And that's exactly what this robot is going to do. This robot now is responsible for handing the address of the bytes to fetch to the shoveling robot. So to start with, this robot is going to start with the program counter, like the place in the recipe, step 1, for example. And he's going to just say, fetch byte 1, then fetch byte 2, then fetch byte 3. And he's just going to keep handing addresses, sequential addresses, to our fetching robot, who then fetches address 1, puts it onto the conveyor belt. And in this extended version, as well as putting the bytes onto the conveyor belt, he also notes down which address they came from, because we need to do some checking later on, and we'll get to that. So now, everything else is pretty much the same, though. So right now, as it started, all we've done is we've added 1 extra stage to our pipeline, which means it takes 1 more cycle, 1 more tick of the clock to start up, and we've got no benefit. But this is where it gets clever. Now, when our executing robot says, hey, we got to a jump or a branch, and he has to pull the ripcord to say, everything needs to restart, he sends a message to the first robot and says, by the way, I got to this point in the code, and then I needed to go somewhere else. I needed to branch to a new location. And our little robot notes that down. So I'm going to make up a really, really simple example, just so that we've got something to talk about. And so our instructions are going to be, and I'm going to say this is like at address 50 in memory, and I'm still using the 6502 based assembly code. Hopefully it's, it doesn't really matter what it is, and the 6502 didn't do this, nor would it need anything like this, but we're sticking with what I know. So I'm just going to have a loop of incrementing the X register, which is a 1-byte instruction, and then the next thing is to jump unconditionally, like every single time, back to address 50, which is a 3-byte instruction. What's this one's EB hex, this is 4C, and then I'm doing this in hex, but whatever. These are the bytes that are actually going to be in our memory cells in sequential memory, which I can draw out in a second. And then it doesn't really matter what's next, but I'm just going to write down that there are some other bytes after this in memory so that we can, and I'm going to put NOPs here. We wouldn't normally do this, it's just so that I've got something to do. So this is EA, I think, EA, there we are. Right, okay. So
just, I mean, it's probably obvious, but NOP is null operation.
It's a no operation, yes. It seems weird that you have to have a recipe step that says do nothing today, you know, have a lie-in, have a nice relax for a clock cycle, but it's very useful for this kind of thing and also for timing and stuff like that. But right now, I've just put those there because I need
just a bit of padding.
Exactly. Exactly. So in our production line, the predicting robot would predict, let's say we already knew that we were starting at number 50. He would predict number 50. He'd hand over 50 to the fetching guy who would fetch the byte. The byte would be put on the conveyor belt. The next robot would decode it as an increment. It would go to the executing robot. Meanwhile, of course, the predicting robot has predicted 51, given it to the fetching robot, 52, 53. These are the bytes over here. So this is byte 50. This is byte 51, 52, 53, 54, 55, or whatever. And he's just happily shoveling out incrementing numbers with no idea at all. It's just like 50, 51, 52, 53, 54, 50. It's the best guess, right? Meanwhile, the increment has gone through, and then the jump instruction's gone through, and eventually gets to the executing robot. So by the time that the third byte of the jump has been decoded by the decode robot, turned into a jump to address 50, handed to the executing robot, the predictor and the fetcher have already fetched these next 2 bytes, and it's been decoded as a NOP. So there's a NOP that's waiting in the pipeline, and there's another NOP that's been, the bytes of it have been loaded onto the conveyor belt. And those are not things we want to do, right? We want to actually go back to the top of the loop. So just to be clear, this jump is an infinite loop that's just going to sit and increment the X register forever. It's a pointless thing to do, but it was just a very straightforward little program for the purposes of this. So the first time this happens, the executing robot pulls the ripcord and says, wait, we're going the wrong way. I need to get back to address 50, please. He sends a message over to the predicting robot, and the predicting robot notes down, oh, interesting. Next time I fetch byte 53, I should actually then start back at 50, because that's what the executing robot has told me. He said, I've got to the end of a jump. I took this jump. The address was 53 because that was noted down on the flow of instructions coming through. And by the way, next time, could you just go straight to 50, please? All right. Mm-hmm. We'll talk about how the predicting robot notes that down. But now you can see that the pipeline is flushed, and then we start again. And so we know that we have to start at 50, and we go to 50. And so now the fetcher's going to do 50, 51, 52, 53. Oh, the predicting robot says, having just predicted 53, I should predict 50 now. And so that's the number he sends to the fetcher. And now the sequence of instructions is just going to keep flowing through correctly, and we won't have any delays while we flush the pipeline, because our executing robot actually peeks ahead and says, well, okay, I would like to jump to address 50. And then before he pulls the ripcord and says, uh-oh, we need to flush the pipeline, he peers ahead and looks at the next instruction. And if it's tagged with address 50, he's like, oh, cool. The predicting robot predicted the correct way. I don't have to pull the ripcord. We just have to carry on. This is great. And so now we've filled up the pipeline with increment, jump, increment, jump, increment, jump, and none of these NOPs make it through anymore. Mm-hmm. So we have predicted for a very, 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 very simple case what's going on. So let's talk about how the robot at the beginning of the pipeline, the predicting robot, how the predicting robot does this job, because I just said he notes it down. But yeah, sure, I could also say, hey, why doesn't he just read the memory himself and just look it up that it's a jump to 50? But that's too much work for a single step of the pipeline. So whatever he does has to be incredibly simple. So first piece of paper off. So there are many ways that this can be done, and in some ways it's similar to caching, which I'm sure there are computer file videos about, or we'll talk about some more another time. But let's just say this is the simplest way that I could think of that's visually straightforward. Let's give the robot a notebook with 10 entries, 0, 1, 2. And in this table, he has a from and a to address. Every time he's told that there is a branch at address, say 53, and I've already thrown that on the floor, So let me put this over here. In this particular instance, I'm using the last byte of the jump instruction itself as being the place, because that's the last one the robot, the fetcher would have to fetch before he had to start going back to address 50. There are different ways to do this, but, oh, and of course I haven't actually put 3 in the table here. Okay, there's 3. ... The robot could search through this whole table every single time and look for, if there's one of these 10 entries that matches the from address, then he could go to the to address. But that's a lot of work, even that. I mean, that's 10 whole steps every single click of the clock, and that's just too much work for our simple predicting robot. So what he does is he looks at the last digit of the address. So in this instance, as he's predicting address 53, he knows to only look in slot 3. Now that means that there could be some other things in there that are the wrong thing, but if it matches, then he's going to take that. So let me work through that, and hopefully that'll make a little bit more sense. So the table starts out empty to begin with. The robot is predicting 50, and as he's predicting 50, he quickly looks in the table and he looks at the last digit of 50, 0. The table entry for 0 is empty. Fine. 51, without anything in the table, he just predicts the next address, right? We're just going to sequentially go from address to address, and so on and so forth. So we get to 54 and 55, and that's when the air horn is pulled, and our friend, the executing robot, says, hey, 53 has a jump to 50. So we will update entry 3 of our table and say, hey, 53 goes to 50. Then we reset, we start again, 0, check, 51, check, 52, check, 53, okay, we're looking in slot 3. Oh, the from address matches for this particular jump. Oh, so I know that instead of incrementing, I'm going to go to address 50. And that's a really simple way of doing it. Now, there are obvious flaws with this simple approach, and that is what happens if there are 2 branches, one at address 53, I want to address 63. They're going to land in the same bucket, and then what we keep doing is overwriting them, and that's a shame, and it's unfortunate. There are limitations to this, and there are ways of improving that. We can have multiple slots in this thing, in this table, but it's a straightforward way, and it gives you a flavor of the kinds of things that are going on inside. In modern CPUs, this is called the BTB, the branch target buffer. And it's a predictor for where the target of a branch is. And in fact, it's also predicting whether there is a branch, because our predicting robot doesn't know anything about the program at all. He doesn't know anything at all. He's just got to increment numbers and occasionally check his table and say, oh, no, actually, we're going to go somewhere else. Now, if you've ever heard of branch prediction before, a lot of it concentrates on predicting whether a branch is taken or not. And in this instance, I've started with an unconditional branch. This always happens, and so it's an easy choice. It always happens, so every time we get to address 53, we want to go back to 50. Fine. What happens if this was a conditional branch? What if it was comparing 2 numbers and it says, well, if the number is greater than 10, do something else not? How can we update this? Well, let's get a very simple example. I'm going to put you over there, and I'm going to work through. Let's say we've got our Fibonacci sequence thing again. Load 1000, x, add 1001, x, store 1002, x, increment x, compare x with, say, 100 to get the 100 Fibonacci numbers, branch if not equal back to 60 at the top here. This is address 60, this will be 63, 66, 69, 70, 72, I think. I'm trying to remember how big each of these, I mean, it doesn't really matter, but it gives us an idea. But, for example, here's the first example where these 2 instructions, 60 and 70, would land in the same table entry. And so if there was a branch in both of those locations, they would fight for each other. But there aren't in this particular example. But what we've got here is a conditional, let's do RTS here, which would be 74. We've got a conditional branch at this point in the table. So let's assume we've actually run one program and then the other, so we're going to use the same bit of paper for the sake of making this easier. What would happen if we just use the approach that we've got so far? Well, we would run through 60, and there'd be nothing there, 61, 62, 63. 63, when we get to the add, we would look in this slot, but we would compare it with 53, and we're like, well, that's not the address of a branch, right? We know that it's not a branch because 53 not equal to 63. So we don't use this particular entry of the table. We keep on going round and round this thing. Eventually we get to this branch. Now, let's say it's the first iteration of the loop, so the branch is definitely taken. When we get to the branch and the executing robot says, wait a second, I did the comparison and we're going to go back to address 60. Here we are at number 72. In this instance, the end of the branch is address 73. Oh, isn't that convenient? That actually wipes out our branch topic buffer over here. So 73 would actually land in this same slot. So this is a good example of evicting something from the branch target buffer, unintentional. He would send a message and say, wait a second, next time you get to 73, go back to 60, please. So our predicting robot would come in, cross out 53 here, and would write 73, and it goes to 60. Brilliant. And then we would go back to 60 and we'd loop round. And of course, when we get to that branch, we would correctly predict that we go to the top of the loop again. And so this is going to work for 100 times. That's great. We've predicted the branch correctly 100 times, or 99 times, I guess, if the first time was a misprediction. And then we get to the problem. On the 100th time, when we don't take that branch, something interesting happens. The executing robot will get to the branch. He will look ahead and go, well, I'm expecting to see address 74 now because I didn't take the branch. But the next thing in the pipeline is actually the load for 60. Oh dear, this is a new kind of emergency situation. Instead of us taking the branch, it's like, well, we took a branch and you didn't guess right. Sorry, Mr. Predictor, you made a mistake. So he pulls the cord and we throw away all the work again. But he also sends a message back to the predictor to say, like, you guessed wrong. And this could also happen, for example, if we've loaded a new program and we actually don't have a branch there anymore, for example. But so in that instance, what the robot would do in this very simple predictor is just cross out these entries and leave them empty again. And then he will next time round, he won't make that prediction. And so that's an okay prediction system. We always predict. Effectively, what we're doing is for every branch, we predict, if it's conditional, that it did the same thing it did last time. Because if we remembered it from the last time and we were re-steered, we go, oh, all right, well, next time I'll predict it to be taken. Or, whoops, no, next time I predict it to be not there at all. And that's not terrible. You know, it's like the old adage about like predicting the weather. You know, yesterday's weather is a perfectly good predictor for today's weather under almost all circumstances. And it's pretty true of most branches. They probably go the same way. Certainly of loops. That is a good guess. If you took it last time, you'll probably take it again because loops often go more than a couple of times and you've already paid back the cost of predicting or mispredicting. But what if we wanted to go a little bit more intelligent? So, you know, maybe, I mean, what would you do if you kept being asked or being told that things are being taken or not taken? How might you think of like trying to make a guess about whether next time something's taken or not?
You could maybe jot how many times you'd done it. I don't know. Would that
Exactly. So yes, what we're going to do, and again, all these things have to be so ludicrously simple that they can be done in one clock cycle by this prediction robot. And I have a prop. You don't know this, but I've got a prop. Hopefully this shows up on the camera. This is like me raiding the kids' toys. They're all grown up now, so that, you know, we've got a basement full of nonsense. Here is our table again, drawn out, or rather doodled onto the side of a toy. Here are our slots, our from and our to, and I've got some validity thing here. That's to say whether or not it's filled in or not, but I'll just use whether I've written in it or not. And so what we're going to do is every time we take a branch, let's copy out my chart from here. What were we? Number 3 was from 73 back to 60. So number 3 was 73. Whoops, now it's not going to write on here. 73 back to 60. And I guess it's valid. I'll tick the box there to say it's valid. There you go. It's an actual branch that we did take. You know, obviously in computing terms, you can't have empty boxes. You have to have a bit somewhere that says, are the boxes empty or not? And that's what this little bit is on the end here. It's like an earlier thing. So we start out with these predictions here, and I have these frowning faces going through to smiling faces, which may not be visible on the camera, but never mind. And this is the number of times that we have either taken or not taken. And every time we take the branch, we move the counter 1 to the right. And every time we don't take the branch, we move it 1 to the left. And then when we have to come and make a prediction, we say, if it's in the left half, we'll assume that it's not taken. And if it's in the right half, we'll assume it is. So we have some kind of track of like it. So like, for example, well, let's say we'll initialize them all as like, we're going to guess that these are referred to as, you know, very unlikely, unlikely, likely, and very likely, something like that. And so we'll assume that it's just likely, slightly likely is our sort of default case. So the very first time we hear about a branch that's conditional, we write it into our table and we initialize its counter to be here. Right, in the somewhat likely case. And then we go around the loop, and then the next iteration around the loop, we predict that it's taken because it's in the somewhat likely camp. And then when we get the feedback, so now our executing unit has to always give us feedback. It doesn't just tell us when we got our prediction wrong and pulled the ripcord. It has to tell us like, hey, yeah, you guessed right, well done, you. And if he says well done, we pick up our counter and we move it over to the right here. And now we're even more likely to predict it. Now, obviously, that means that next time around we're definitely going to predict it. In our particular example that we just explained here with the loop of 100, when we get to that 100th iteration and we make a mistake and we go, yeah, we're predicting it, instead of throwing away our work, the executor robot says, hey, you guessed wrong. We didn't take that branch this time. And we go, oh, well, I guess we're going to move you back down to only slightly likely. And that's pretty cool, because if we were to re-execute our Fibonacci loop, it's still the case that the next time we run it, we probably start from 0 again, that we do actually want to predict it was taken. Without this counter here, we would have just said, no, it's not taken immediately. We'd have just predicted the same way as last time. But here we have a little bit of hysteresis. We've got a little bit of a memory about how this has gone before, and it's still extremely straightforward for a system. This is just 2 bits inside this otherwise quite large table that predicts whether or not we're going to take. And obviously, if it was a more complicated conditional conditional branch, then eventually we might learn that it's not taken ever again. We keep going back until it's like, no, never predict this as being taken. That's kind of the simplest form of this sort of branch prediction. With the conditional part of it, like those deciding whether this branch is taken or not. So this branch target buffer here, which I'm representing, has 2 jobs. The first thing is there a branch at all? And the second thing is, should it be taken? Should we predict that it's taken this time? And obviously you can just, if you get an unconditional branch, you could use this same table and just initialize it as, extremely likely, like if there's a branch up here. But in practice, they're done separately. And so this is great, but there are a lot of things even that this doesn't cover. And so just to give you a flavor of the way that modern processors work, what modern processors tend to do is they separate these 2 tables out. They have the predictions in one table that's much bigger because it's only these 2 bits for every entry in the table. And then they have the from and the to. And then they use a combination of where the branch was, the history of the last few branches that have been taken, like for every time we take a branch, we add a 1 to like a register that's being shifted along. And every time we don't take a branch, we put a 0. So we've kind of got like a pattern of like what's happened recently. And we smush all those bits together with like a very simple hashing algorithm to get like a unique fingerprint for when I got to this branch and I had taken the previous 3 branches and I had not taken the branch immediately before that, then I go and look at a particular entry in my likely or unlikely table, and then I will update and use that for my prediction. And that allows the branch predictor to take into account patterns in sequences. So for example, if 2 things are correlated, as they often are, then the branch predictor will learn that if you take this branch, you're almost certainly not going to take this other branch because that will be in the pattern and it will be in the history. So it's kind of like a very straightforward learning system. And it's remarkably good at predicting the flow, which, as I've said before, is really important with modern CPUs where this pipeline isn't the 3 or 4 steps that I've described. It's many steps. And it gets even more important to get this right when we start adding more and more execution units, that is more and more robots at the end of the pipeline that can do lots of work simultaneously.
Can I ask a question? Is there a situation where, no matter how complicated or impressive this is, that it just doesn't improve things?
Absolutely, yes. Yes, there absolutely is. So there are pathological cases for certain. So things that can't be predicted are like random events. Random events can't be predicted, and so the pipeline is got, at best 50-50 chance of getting things right, in which case, you're throwing away work half the time. It's still no worse than if you didn't do prediction at all, because you'd still be wrong a lot of the time, but it can be considerably slower than a branch that is predicted. So for example, actually, there's a I wrote a ray tracer, which I'm sure you've covered before. And one of the things you do when you're ray tracing is you take a line in space and you intersect it with a triangle and see if does this line cross through this triangle. And for any one individual triangle, you're very unlikely to hit the triangle with any particular line. This is in 3 dimensions. And one of the checks is, am I off to the right of the triangle, or I am off the left side of the triangle, right? And each of those is a comparison and a check. Now, for any random triangle and any random line, it's literally a random chance of whether it's off the left or off the right. And so the branch predictor there can't get it right. It's like, hey, you just gave me a ray that's anywhere in 3D space, and it turns out that it's off the right, but it's just as likely to be off the left, right? And that's unpredictable, and that's hugely slow to predict. But if you combine those two comparisons together and say, is it off the left or is it off the right together, and then do a branch off of the pair of those things combined, that branch is very, very predictable, because it's almost always, yes, like you didn't hit the triangle, branch away, skip this triangle, go to the next triangle. Right. And so a tiny, literally 1 character change in my source code for the ray tracer sped it up by 30 or 40%, because this was in the deep core loop of the rendering loop. And it was just really fascinating and really interesting sort of to be able to track that down and trace it right back to the predictor inside the CPU. Metronome clicks before that particular thing has finished. But what you'll notice is that if we can keep it fed,
therefore we can calculate the lighting effects. And it's why I'm able to have a shadow here, because...
So when we left off, we had accomplished building a pipeline CPU that effectively gave us a scalar processor. And we said that a scalar processor meant that we could effectively achieve an output of 1 instruction per CPU cycle, because we had multiple instructions, in the CPU at the same time. So now we want to look past that. We want to build what's known as a superscalar processor, or a processor that can actually achieve an output of more than 1 instruction per clock cycle. Now, how do we do that? Well, the answer lies in a few areas. First of all, remember our fetch. We said that we're going to grab multiple instructions from memory at the same time and keep them in a buffer. Well, we're going to make sure that we're doing that enough to support running multiple instructions at the same time. That's the big first step. So we're going to need enough in that buffer to keep the CPU happy so that it can chew on multiple instructions. We're also then going to break apart our fetch and decode so that we can decode multiple instructions at the same time. And we're going to have parallel execution units. This means that we might have multiple ALUs. We might have ALUs that specialize in things like integer math, and other ones that specialize in floating point math. There's going to be lots of specialized hardware that will be better at serving a purpose, doing specific instructions, but not others. And we need smart decode that actually knows then to pass those particular instructions to those specialized execution units. Because of this, we're going to have an output, hopefully, of more than 1 instruction per CPU cycle. In fact, modern CPUs do in fact use this, and they usually achieve a 2 to 5x improvement of 2 to 5 instructions completed per clock cycle. So if you imagine, if we go back to that 4 gigahertz CPU that we were using as an example before, if we achieved the high end of this, if we achieved a 5x return, we would actually be pumping out 20 billion instructions per second on a 4 gigahertz CPU. So let's visualize this. Up top here, we have a scalar processor, right? So this is the standard pipeline. Instruction 1 goes in, it's fetched and decoded. Now notice that the fetches all happen at the same time. We've changed this up a little bit from the one that we looked at last. I said that now we're thinking of grabbing stuff from memory in batches, right? So in effect, all of these instructions are actually fetched in the same cycle, because we grabbed a whole bunch of information from memory and put it in that buffer. But we can still, in a scalar processor, only decode 1 instruction per cycle. So on clock cycle 2 here, we decode the first. On clock cycle 3, we execute the first, decode the second. And then on a clock cycle 4, we write back, execute, decode, and this pattern continues. And you can tell that we do get to a place now, like if a new instruction had started down here, we do get to a place where we're working on 4 instructions at any given time. Now, again, this is only showing instructions of the same length, and we're not dealing with bubbles and other problems, but it's just the theory. Now, a superscalar processor is one that has multiple decode and multiple execution and write back features in its hardware. So in this simple example here, we're just going to assume that the hardware can work on 2 instructions at one time. So we still get all 4 instructions here with 1 fetch, just like we did before. But this time we decode 2 and we execute 2 at the same time we're decoding the next 2. And we do the write back here while we're executing these 2. And this pattern would continue, and now you can accomplish twice as many things in 1 instruction cycle, or 1 clock cycle. In fact, you'll have an output if there's no problems here, no branching, nothing goes wrong. You'll have an output of 2 instructions per clock cycle. So let's look at a breakdown of what this actually looks like in the hardware if we group the hardware together. So we have here this instruction unit that's basically going to decode the instructions and make decisions on where they should go once they're decoded. And we're going to specialize execution units that it can choose from based upon the decode. So if, for example, the decode is a branch, it's going to give it to this branch processing unit that is specially engineered to deal with branches as efficiently as possible. We also have here a load store unit, which really is kind of a way to offload stuff that you're going to put into registers, and it can deal with all of the actual logic of moving things with the registers. And then we have specialized integer processing ALUs, floating point ALUs, etc. Now, it's also important to note there's no law that says you can only have 1 of these. So if you predict that, say, you'll be doing more integer math than, say, floating point math, you might have multiple floating point ones as well. An important part of this now, 2 things I want to point out. One is that notice often the registers are shared between different units, right? That's important to keep in mind, that even though we might have multiple ALUs, we still might be sharing the same registers. Another thing that's really important to point out is this completion unit. So what's happening here is, remember we talked about last time, even though we're speeding things up, all instructions still have to come out of the CPU in the correct order. And we can't introduce bugs at the hardware level because we did things out of order. So it's very important that we have, and this is a very complex circuit, logic here that ensures that that is the case, that we're actually gluing everything back in the correct order as the CPU outputs the results of its work. So some issues that we might run into in the superscalar world, this is kind of a growth of the issues that we talked about in the scalar world when we talked about branching and things of that nature. So one is out of order processing. So if we're creating pathways for multiple instructions to go down at the same time, we are going to have to deal with the fact that some of those instructions might have had a dependency on other instructions that went down a different path, right? This is something we talked about in the scalar world as well, but now in the superscalar world, it becomes even more prevalent. We're also going to have issues with control dependencies. So if we have a branch change, or if flow of the program changes, that's going to affect all of these execution units. So how do we deal with that? Well, this is actually a more complicated problem than it was when we just talked about it in the scalar world. In the scalar world, we only had the one pipeline, and we could effectively say, okay, if we can try predictive, and if that failed us, we would have to flush the pipeline and start it over. But since we have multiple execution units, another way we could do this is to use multiple execution units to effectively play out both scenarios. we could actually pretend, let's fill a pipeline up with what happens if we do branch, and let's fill a pipeline up with what happens if we don't branch. This is called speculative execution. And at the end of the day, whichever one is right, we keep, and then we throw away the other one. This can also be used with branch prediction, just like we talked about in the scalar world. So we can still keep that as part of our tool in our toolbox, but we expand upon it by actually keeping now a branch history table that's a little bit more complex in the modern circuitry that aids in our branch prediction. So it will be even more accurate than just kind of guessing without the table. We can also have issues with conflicting access to registers. So remember, when we looked here at the diagram, our general purpose registers were shared between multiple units, and this really just shows the load store unit. But in reality, there could be other circuits that are connected to these registers besides this integer processing unit and the load store unit. And you might need to have more than one of those use the registers at the same time. That's obviously going to cause a delay for at least one of those two instructions.
So those are the references that you can watch during your spare time. No? So I have here in my presentation the links, no, for you to watch during your spare time. So that's our slides and presentations for today. No? Again, before we end this presentation, our subject, here's the recap. So today we were able to tackle embedded systems, wherein this refers to the electronics and software within a product. No? For example, cell phones. Meron din tayo ditong mga security systems, calculators. No? These embedded systems are, have their own firmware software embedded. That's the idea behind it. So these are some of the numerous types of sensors and actuators in automated systems. Again, cell phones, washing machines. Pinakamagandang example ng embedded systems na meron tayo is yung cell phone. No? So on the right hand, ito again yung sample architecture ng embedded systems natin. So the comparison between microprocessor and microcontroller. Yung microprocessor kasi, ang meron lang sa kanya is arithmetic logic unit, control unit, and registers. On the other hand, yung microcontroller, it's like a mini computer wherein it has a temporary data or memory. Meron din siyang input-output ports, meron siyang clock, and meron na rin siyang converter like analog to digital and digital to analog converter. No? So that's the differences. So we have various categories on how we can maximize or overclock our microprocessor. We have the pipelining, branch prediction, superscalar execution, speculative execution, and data flow analysis. Included in these slides are again the references that you can read during your spare time, before our exams. We still have 2 weeks naman for our exam, but again, these are some of the important lessons that you have to study. If you don't have any more concerns, I think that's good for today. It's almost 8 na rin naman. So if you have questions, don't hesitate to message me on my messenger or chat nyo na lang si yung mga class president. So again, the next meeting would be about clock speed and how clock speed could help us in our designing computers and organizing some of the components. So thank you very much. See you again next week.